In the last class, we saw the usage of the equation F is equal to ma. Now, we will look at this equation in a new form, and this formulation is referred to as the work and kinetic energy formulation, which leads to the principle of conservation of energy. So, in order to see this, let us introduce two new concepts. We will introduce the concept of work and the concept of kinetic energy. So, these are two terms which will be defined in the sense of physics in today's class. So, first we define the term work, and when we talk of work, we talk of work done by a force. So, we have a particle or a body on which a force acts, and in general, if this is the only force acting on this body, then the body will start to move with an acceleration a in the direction of the force. Of course, more than one forces could be acting on a body. Now, what we are going to do is, let us define the term work done by a force. And what happens is, to define work done by a force, we need two things. Firstly, we need to know the force, which we know is a vector, and then what we know is, if what we also need is, if the if due to the action of this force the body undergoes a displacement d. And what we will do is, let us start this in a simple sense by looking at the one dimensional case first. So, we start with a one dimensional case, and so that we have a particle, a force F is applied, and because of this the particle undergoes a displacement d. So, we define the work done as the product of the force and the displacement d. So, in this case, when a particle undergoes, so we are talking of a 1D case, so force is in this direction, and because of this the particle moves a distance d in the same direction. So, the work done by this force is defined as F times d. So, this is the definition of work done by a force. So, which means that to be able to define work done, we need two quantities. We need the force which is acting, and this will be work done by this force, and the effective displacement of the body which it undergoes while this force is acting on this. So, that will be called the work done by force F. So, work done by force F is the product of the magnitude of force and the magnitude of displacement, and this we should say this is for a one dimensional case. We will generalize this to a two dimensional case slightly later. So, now let us talk in terms of vectors. So, we have a force F which is acting, because of which particle undergoes, so this is the particle which I am showing as a dot, it undergoes a displacement R. So, therefore, for the 1D case, work done will be equal to magnitude of F times magnitude of R. Now, it can so happen that n forces can act on the body simultaneously. So, let us say we have a body on which, so we have a force F1, a force F2 and so on. So, different forces act on the same body. So, now we will have work done by F1, work done by F2 and so on. So, each force will do a work on the body and the work done will be given by the product of force times the displacement. Now, let us generalize this concept. We talked of a 1D case and we generalize this, and in a general case, let us say we have this particle on which the force F is acting, and particle, let us say there may be more forces acting. So, therefore, we are looking at the work done by this particular force, let us say F1. Now, if the particle is moving like this, let the displacement of the particle be given by R, and so the angle between the force F and the displacement R is phi. So, now for a general case we have three quantities, the force F or F1 is the force, R is the displacement, and actually we know the two vectors F and R, angle phi is known, and phi is the angle between F and R. And in this case we define, for this case, the work done by W is the work done by F1, and this is given by magnitude of F1 times magnitude of R times cosine of phi. So, this is how we define work done in a general case when force and displacement can be along different directions. And if we realize this is nothing but the dot product of force and the displacement vectors. So, therefore, what we see is the work done by a force F, this will be equal to force dotted with the displacement vector, where R is equal to the displacement vector. And this we have also seen is equal to magnitude of F times magnitude of R times cosine phi. So, F is the force, R is the displacement, this is phi. Now, from here what we see is some special cases, if phi is equal to 90 degrees, if the force is acting perpendicular to the displacement, then work done will be 0. If phi is greater than 90 degrees, then cosine of phi will be negative and work done will be less than 0. Also from here what we realize is that work done, so this is how we define work done by a force in a generalized way. So, work done by a force is equal to F dotted with R. Sometimes we use the vector D for displacement, and if we do that, then work done will be equal to F dotted with D. Now, work done, you realize from this is a scalar. F and D these are vectors, but work done is a scalar, and this is a scalar which can be either 0, positive or negative depending on the angle between F and D. And if we look at the units of work, the SI unit of work done, this will be equal to SI unit of force multiplied by SI unit of distance. So, that will be equal to Newton times meter, and this we also write as joule. So, 1 joule is equal to 1 Newton meter, and in SI units we write work done in Newton meters. Sometimes when we deal on an atomic scale, then the unit of work done is written in terms of electron volts, and 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joules. So, when we work at atomic levels, then we use the unit of electron volt, so that we do not carry too many small powers of 10 when we work. Now, let us look at some simple examples to define this concept of work. A student lifts a rock of mass 10 kg from the floor to raise it to a height of 2 meters with negligible acceleration. So, we are assuming that there is a stone or a rock lying on the ground, and somebody lifts it from the ground up to a height of 2 meters with very negligible acceleration. And the reason for this is we do not want any force to come on the body because of this. So, now if we look at this, what we want to find out is, so we want to identify firstly the force, the different forces acting on the rock when the student is lifting it, and secondly we want to find the work done by each of these forces. So, a very simple problem, we just want to, this is to illustrate how to calculate the work done. Let us find the work done by each of these forces. So, the work done by gravity is, gravity force is mg, it is moving up, the displacement is 2 meters, and so therefore, the angle phi is equal to 180 degrees. So, work done by gravity is equal to mg multiplied by 2 multiplied by minus 1, and this will be equal to minus 196 joules. So, work done by gravity is minus 196 joules. Work done by force F which the student is applying. So, for this F is equal to mg, d is equal to 2 and phi is equal to 0 degrees, because now force is acting in this direction, displacement is the same. So, therefore, now this work done by F, this quantity is equal to mg times 2, and this will be equal to plus 196 joules. So, now of course, you will realize here the total work done on the rock by the forces, by I will say external forces, this will be equal to 196 minus 196 is equal to 0 joules. and this we should have expected because the total net force on the external force on the rock was 0. So, therefore, the work done also has to be 0. But individually there is work done by gravity, individually there is work done by the force which the student is applying, and each of them they are negative, so they cancel out. Let us look at one more simple example. We have a block of mass m on a floor with friction. A force F is applied on a crate or a block of mass m, and the coefficient of kinetic friction between the block and the ground is given by mu k. It is also given that the block moves with a constant velocity and moves a distance d. So, it moves with a constant velocity and it moves over a distance d. So, it starts from here, let us say it has moved a distance d. So, this is the final position of the block. Now, once again the question says, or let us try to identify the different forces on the crate and their magnitude in terms of the given quantities. We have the block m mass given, gravity of course is there, and the distance d is given, the coefficient of friction mu k is given. So, we have to identify the forces on the crate, and then we have to find the work done by each of these forces. So, now what we do is, first thing what we should do, since we have to identify the forces on the crate, as in any problem, let us draw the free body diagram of the crate. When we draw the free body diagram, so this is the block or the crate, then we have the weight mg acting down, reaction from the ground which is coming, so we put it as normal reaction n. We have the force F which is being applied on the block, and we have the force of friction, which I right now indicate as small f. So, these are the different forces acting on the block. So, this is the free body diagram of the block. These are the forces. Now, we have to identify the magnitude. Now, what is given to us? Let us see, it is given to us that the block is moving with a constant velocity. If the block, so since acceleration of the block is equal to 0, that means sum of forces in the x direction have to be 0. Obviously, sum of forces in the y direction are 0 because the block is moving in a horizontal direction. So, there is no acceleration in the y direction. So, this is our x direction, this is our y direction. Now, when I write this, what I get is mg is equal to n. That means the normal reaction, which is an unknown, this is equal to m times g. And also what we know is this force F is equal to the force of friction. Now, what we also know is our laws of friction, because the block is moving. So, that means there is relative motion. So, therefore, friction, let us put it here, since there is relative motion between the block and the surface, the friction force F is equal to mu k times n. So, this will be equal to mu k times n was equal to mg, it is equal to mu k times mg, and the force F is equal to F, the friction force. So, that also must be equal to mu k times mg. So, that means totally we have 4 forces acting on the block. Let us list all of them: A, mg which is acting downwards, B normal reaction which is acting upwards which is equal to mg, C the force F which is being applied in the forward direction and this is equal to mu k times mg, and fourth F the force of friction which is acting in the minus x direction and this is equal to mu k times mg. So, we have these 4 forces acting on the block. Now, we have to find out the work done by each of these 4 forces. So, this is part A of the problem. Part B is we have to find the work done by each of these 4 forces. So, work done. Now, what we realize is the displacement of the block d or r vector, if we write this is in the x direction, this is equal to d times, we can write it as di, it is d distance in the x direction. Now, mg and n, they act in a direction perpendicular to the displacement d. So, therefore, work done by n and work done by mg is equal to 0. Now, notice this work done depends on the dot product of force and the displacement. So, once we are trying to calculate the work done, we look at the particular force and the displacement which will stay the same for all the 4 forces. And so, because these 2 forces are perpendicular to d, work done is equal to 0 by these 2 forces individually. Of course, we also know n is equal to mg. So, therefore, if you and they cancel out. So, if you add these 2, the work done would have been 0 even if the particle was, if this they were equal and the particle was moving vertically, net work done by these 2 forces would be 0. But here individually also the work done is 0. Now, we look in the at the other 2 forces in the x direction. So, forces in the x direction. So, work done by F, the external force, and work done by F, which is friction. So, this will be equal to, now again we use the formula, work done is F times d times cosine phi. So, if we use this formula, then work done by F is equal to F times d, and since this is in the direction, so we have cosine of 0 degrees. So, this will be F times d. So, this is mu k mg times d. Now, when we look at friction, friction is acting in this direction, the displacement d is in the plus I direction. So, here what we have work done by friction will be equal to friction force times d times cosine of 180 degrees, and this will be equal to minus of mu k times mg times d. So, these are the work done by 4 individual forces. Work done by n and mg separately is 0, work done by F is equal to mu k times mg times d, and work done by friction is equal to minus mu k times mg times d. What you also realize is if you add up these all the 4 work done by different forces, you get a 0, and that is so because the next external force on the body is equal to 0. So, there is no acceleration. So, even though the body moves, the net work done when the body moves is 0. So, this is how we work out the total work done by individual forces and work done as a resultant of all these. Maybe we can just have a look at another example where we have an inclined slope, we have a block of mass m, and this is being pulled with a string over a pulley. This incline is at an angle theta, the string is pulling, and this, so there is a string tied to a winch. So, this we are pulling up. So, the winch, this goes to the winch, as the winch rolls the string pulls up the block. So, block being pulled up an incline. This incline is straight and block moves a distance d. So, now and this angle of the ramp is theta. Now, what we want to find is, so we have a block being moved up a ramp on a frictionless surface with constant speed for a distance d. And we want to find the force F which cable must exert, and the work done by the force F, by the cable force F, so that the block moves a distance d. Then we want to find the work done by gravity during this process, and we finally pose the question, if the block were to move vertically by the same height h, which is equal to d sin theta. That means, if instead of going on a ramp, it was vertically lifted at the same height. So, this is d, the vertical height the block moves up is d sin theta. So, if the block were to be be carried up by a height h is equal to d sin theta, what would be the work done by gravity? Now, we draw the free body diagram of the block. So, we have the cable force F which is exerted here, we have the weight mg, and we have the normal reaction, the force being exerted by the ground on the block. So, this is the ground, it exerts a normal reaction. And now, here if we now draw, so what we can do is we can choose this as a x direction. So, we can resolve mg along x and y. So, what we will get is, we write this, this is n, this is f, and what we will have is mg sin theta and mg cos theta. So, what we have done here is mg was vertical, this angle was theta. So, we write the component along y as mg cos theta, the component along x as mg sin theta. And from here what we get is n is equal to mg cos theta, f is equal to mg sin theta. So, now to find the work done by F, so work done by the force F, this will be equal to the force F mg sin theta times the displacement d times cosine of 0, which is 1. So, that will be equal to mg sin theta times d. Now, the work done by gravity, so here the force is mg, the force in gravity here is mg, the displacement d which is there, so the displacement is d, and cosine phi, we look at this, the angle phi here. So, we have to find the angle between this and the displacement. This angle is theta, this angle is 90. So, this will be equal to times cosine of 90 plus theta. So, this will become equal to minus mgd sin theta. So, the work done by gravity is minus mgd sin theta. And if we look at the last part, that is, if the block were to be lifted vertically up by a distance h is equal to d sin theta, then the work done by gravity would have been equal to mg multiplied by d sin theta, and because it is being lifted upwards, mg is in the downward direction, this would be upwards. So, we would get minus 1. So, this would be again equal to minus mg times d times sin theta. And the point we realize here is whether the block is being lifted along the incline or is being lifted vertically, as long as its initial and final positions are the same, the work done by gravity is the same in this case. So, the general method to find the work done, when you have to apply the method of work, which we will discuss later, to these problems, first you draw a free body diagram of the particle, and then you identify. So, this will identify the forces acting on the particle, and these forces will be along with their directions. Some of these forces will be known, some of them will be unknown, and they will come by a force balance. And the other thing which you will have to do is then you find the displacement vector d, or sometimes we use r, of the particle. And then you find the third thing you will need is the angle between each of these forces, I call it Fi and d. D will stay same for all the forces, and if this angle is phi, then work done by F sub I will be equal to magnitude of Fi magnitude of d times, let us call it as phi I, cosine of phi I. Notice this phi has an I because each force will have a separate angle with the displacement d. So, this is how we then calculate the work done, as simple. And what we realize is when you do this, there will be a sign of W. That means W can be 0, positive or negative. W can have a negative sign depending on the force which is doing work on the cable. Now, this definition of work done we have done has been for assuming that force F is a constant. But we could have a case where force F is not constant. It may be a function of the displacement. And in that case, we will have to now then generalize the concept of work done even further, and that is what we will now do. So, let us look at a case of first a one dimensional variable force. That means the force and the displacement are along the same line. So, if this is the force, the displacement is also here, and let us say this direction is the x direction. So, the same line which we take it as the x axis or the x direction. And let us say the force F depends on the displacement, and the displacement we show as x. And this we can show it in a graphical form. We have a force as a function of x, and force is varying with x. So far what we had done, simple examples, we had assumed that the force F was constant. So now we also, let us say the particle under the influence of F moves from xi to xf. This was its initial position and it comes to this final position xf. So, what we do is we divide this region from xi to xf we divide in small displacements of delta x. So, I choose a small displacement delta x, and over this region let the average force on the region delta x be equal to f bar of x. So, this is we are at some distance x away, and there the displacement, we look at a small displacement delta x, let the average force be f bar of x. So, the work done in this small interval delta x. So, over this small interval delta x, the work done will be equal to f bar of x times delta x, because the average force here is f bar, the displacement is delta x. So, the work done will be f bar of x times delta x, and this you will see is the area of this small strip which I have shown as shaded. So, now the total work done, this is, we can write this as delta w, this is the work done over the small interval delta x, this is equal to f bar of x times delta x. So, therefore, the total work done this will be summing over all these boxes. So, I start from xi, go to xf, make small boxes of delta x each, and then the force at each of these is f bar, which is a function of this x, and then I take all these small rectangles, I add up the area. So, the total work done is sum of all these, this I can write it as sigma over f bar of x delta x, summation over all these intervals, and in the limit delta x goes to 0, this summation becomes what we call as the integral, and so therefore, what we have is the total work done is equal to integral from xi to xf f of x dx. So, therefore, based on this we say the work done is the area under the f of x versus x curve, and so work is an integral of force vis-a-vis the displacement. So, if we integrate the force with respect to x from xi to xf, we get the work done by this force. Now, there is a particular special case where we have a force called the spring force. We have seen this, if there is a spring which is there. So, this is an uncompressed spring, and the position when it is uncompressed, that is where we define. So, our x axis is at the uncompressed position of the spring. Now, what we know about a spring is that if we compress or stretch the spring, a force is applied by the spring, and the spring force, if I write it f of x, is a function of x. So, now x is equal to 0 is the uncompressed position of the spring. So, when x is 0, there is no force of the spring, but if that means, let me draw this again. So, this was the spring, this is uncompressed. So, if I either stretch the spring, so if I stretch the spring, that means this is the x, this is stretched position, and the force which the spring applies is a function of x. And similarly, if I compress the spring, so now here this is compression, so x is negative. In both these cases, whether I stretch the spring or compress the spring, a force F is applied. And by Hooke's law, what we have is the force on the spring is given as minus kx. K is called the spring constant, which is greater than 0, and the such springs where this force F is proportional to the extension or the compression of the spring, to the displacement of the spring. So, this is a particular type of spring, and the force which the spring applies is equal to minus kx. And what we have is, so f of x for a spring is equal to minus kx, x greater than 0 means extension, x less than 0 is compression, and x is equal to 0 is the position of the relaxed spring, and there is no extension or compression. The SI units of K are Newton per meter. Now, let us see if the spring changes from xi, the initial position, to xf. Now, xi could be 0. If it is 0, that means we are starting from an unstretched position of the spring. If xi is positive, that means we are starting from already a stretched position, and xf could be a bigger positive number, could be a lesser positive number, or could be a negative number. Both of these can be anything xi to xf, and then we want to find the work done by the spring force. If the spring undergoes the change of configuration from xi to xf, then the work done by the spring force, so this will be equal to integral from xi to xf, force due to the spring times dx. So, this will be integral from xi to xf, force due to the spring is minus k times x dx. So, this becomes equal to minus k times integral from xi to xf x dx. So, this will be equal to minus k by 2 times x square xi to xf, and this becomes equal to finally half k times, because of the minus sign, we get xi square first minus xf square, and this is the work done by the spring. Now, if xi is 0, then we will just get the work done by the spring will be minus half k xf square. Now, notice, because xi and xf in the work done term in a spring come as square, so it will not matter whether the spring is compressed or stretched. As far as the work done goes, the sign will still stay to be the same. Another thing we realize in this is that the length of the spring does not come into picture. It does not come into picture in an explicit way, it comes in an implicit way, because k is a function of the length of the spring. But otherwise xi and xf have to do with the compression of the spring or the extension with respect to its neutral position. So, whether the spring is 1 meter long or 2 meter long, as far as the formula for the work done goes, there will be no distinction. So, we have now seen this concept of work done by a force. You will realize one thing, because we are talking of displacement, then we see that work done by a force is equal to F times d times cosine phi, and because the displacement comes into picture, so the work done depends on the reference frame in which we are observing the movement of the particle. It is not a frame independent quantity as force is. Force stays the same in all reference frames, but things like displacement, velocity, these properties are a function of the reference frame. For example, if something is if a passenger is sitting in the train seat, and if we are looking at we are observing his motion or her motion of a passenger who is sitting on the train seat with respect to the train, then the velocity of the passenger is 0, the displacement of the passenger is 0. But if the same passenger is observed from a ground frame, then we see the passenger moving away with the speed of the train. So, clearly work done, when we talk of, is a frame dependent quantity, and this is unlike forces. Any force which is acting on a body is not a function of the reference frame. Now, as a last thing today, let us define the concept of a new concept of kinetic energy. And kinetic energy is something we define. This is a property of a body which a body gets by virtue of its speed. So, if a body moves with a speed v, then kinetic energy, we use the symbol K, kinetic energy K is defined as half m times v square, where m is the mass of the particle or mass of the body and v is the speed of the body. So, kinetic energy is defined as half mv square, and we can also write it as half m times vector v dotted with vector v, it's speed square, and if we know the velocity v, so v is the velocity of the particle, small v was the speed of the particle, and what we know is v square is equal to the dot product of the velocity with itself. So, kinetic energy is equal to half mv square. Clearly from the definition of kinetic energy of the body has to be either greater than or equal to 0. If the mass of the body is negligible, then kinetic energy will be 0. If the speed is negligible, then kinetic energy will be 0. Otherwise, if the speed is not negligible and the mass is not negligible, then kinetic energy has to be a positive quantity. And if we look at the kinetic energy, its unit of kinetic energy, unit of K, this will be equal to the same as the unit of work done, and that is equal to joules, and this can be checked. This will be equal to m is kg, v square means meter square per second square, and this is the same unit which you will get for work done, which is joules. So, in SI units, the unit of kinetic energy is joules. Now, once again you will realize kinetic energy being dependent on the speed is a frame dependent quantity. So, kinetic energy is also dependent on the reference frame, and the reason why we lay a stress on this reference frame is we know that when we apply Newton's law say F is equal to ma, and they are valid only when acceleration is being measured with respect to an inertial frame of reference or a frame which is not accelerating. So, therefore, when we talk of kinetic energy and work done, again I have specified both of these are frame dependent quantities. Now, what we are going to do in the next class is we will look at how work and kinetic energy are related to Newton's second law, and this we will put in the form of a theorem which is called the work energy theorem, which also leads to, for some special cases, the principle of conservation of energy. And we will see that this kinetic energy can therefore thus be related to the force, acceleration which we have seen, and in an integrated form. These details we will see in the next class, where we will see the work energy theorem.